Electron affinity. In chemistry and atomic physics, the electron affinity of an atom or molecule is defined as the amount of energy released or spent when an electron is added to a neutral atom or molecule in the gaseous state to form a negative ion. In solid-state physics, the electron affinity for a surface is defined somewhat differently. This property is measured for atoms and molecules in the gaseous state only, since in a solid or liquid state their energy levels would be changed by contact with other atoms or molecules. A list of the electron affinities was used by Robert S. Mulliken to develop an electronegativity scale for atoms, equal to the average of the electron affinity and ionization potential. Other theoretical concepts that use electron affinity include electronic chemical potential and chemical hardness. Another example, a molecule or atom that has a more positive value of electron affinity than another is often called an electron acceptor and the less positive an electron donor. Together they may undergo charge transfer reactions. To use electron affinities properly, it is essential to keep track of sign. For any reaction that releases energy, the change delta E in total energy has a negative value and the reaction is called an exothermic process. Electron capture for almost all non-noble gas atoms involves the release of energy and thus are exothermic. The positive values that are listed in tables of EEA are amounts or magnitudes. It is the word, released within the definition energy released that supplies the negative sign to delta E. Confusion arises in mistaking EEA for a change in energy, delta E, in which case the positive values listed in tables would be for an not exothermic process. The relation between the two is EEA equals delta E. However, if the value assigned to EEA is negative, the negative sign implies a reversal of direction, and energy is required to attach an electron. In this case, the electron capture is an endothermic process and the relationship, EEA equals delta E is still valid. Negative values typically arise for the capture of a second electron, but also for the nitrogen atom. The usual expression for calculating EEA when an electron is attached is. This expression does follow the convention delta X equals XX since delta E equals E, equals EE. Equivalently, electron affinity can also be defined as the amount of energy required to detach an electron from the atom while it holds a single excess electron, thus making the atom a negative ion, i.e. the energy change for the process. If the same table is employed for the forward and reverse reactions, without switching signs, care must be taken to apply the correct definition to the corresponding direction, attachment, or detachment. Since almost all detachments and amount of energy listed on the table, those detachment reactions are endothermic, or delta E0. Although EEA varies greatly across the periodic table, some patterns emerge. Generally, nonmetals have more positive EEA than metals. Atoms whose anions are more stable than neutral atoms have a greater EEA. Chlorine most strongly attracts extra electrons, mercury most weakly attracts an extra electron. The electron affinities of the noble gases have not been conclusively measured, so they may or may not have slightly negative values. EEA generally increases across a period in the periodic table prior to reaching group 18. This is caused by the filling of the valence shell of the atom. A group 17 atom releases more energy than a group 1 atom on gaining an electron because it obtains a filled valence shell and therefore is more stable. In group 18, the valence shell is full, meaning that added electrons are unstable, tending to be ejected very quickly. Counterintuitively, EEA does not decrease when progressing down the rows of the periodic table, as can be clearly seen in the group 2 data. Thus, electron affinity follows the same left-right trend as electronegativity, but not the up-down trend. The following data are quoted in kJ/mol. The electron affinity of molecules is a complicated function of their electronic structure. For instance, the electron affinity for benzene is negative, as is that of naphthalene, while those of anthracene, phenanthrene and pyrene are positive. In silico experiments show that the electron affinity of hexacyanobenzene surpasses that of fullerene. In the field of solid-state physics, the electron affinity is defined differently than in chemistry and atomic physics. For a semiconductor vacuum interface, electron affinity, typically denoted by EEA or Chi, is defined as the energy obtained by moving an electron from the vacuum just outside the semiconductor to the bottom of the conduction band just inside the semiconductor. In an intrinsic semiconductor at absolute zero, this concept is functionally analogous to the chemistry definition of electron affinity, since an added electron will spontaneously go to the bottom of the conduction band. At non-zero temperature, and for other materials, the analogy does not hold since an added electron will instead go to the Fermi level on average. In any case, the value of the electron affinity of a solid substance is very different from the chemistry and atomic physics electron affinity value for an atom of the same substance in gas phase. For example, a silicon crystal surface has electron affinity 4.05 eV, whereas an isolated silicon atom has electron affinity 1.39 eV. The electron affinity of a surface is closely related to, but distinct from, its work function. The work function is the thermodynamic work that can be obtained by reversibly, isothermally moving an electron from the vacuum to the material. This thermodynamic electron goes to the Fermi level on average, not the conduction band edge. W equals E V A C E F \display style W equals E underscore \, RM vac E underscore \, RMF. While the work function of a semiconductor can be changed by doping, the electron affinity ideally does not change with doping, and so it is closer to being a material constant. However, like work function, the electron affinity does depend on the surface termination and is strictly a surface property. In semiconductor physics, the primary use of the electron affinity is not actually in the analysis of semiconductor vacuum surfaces, but rather in heuristic electron affinity rules for estimating the band bending that occurs at the interface of two materials, in particular metal semiconductor junctions and semiconductor heterojunctions. In certain circumstances, the electron affinity may become negative. Often negative electron affinity is desired to obtain efficient cathodes that can supply electrons to the vacuum with little energy loss. The observed electron yield as a function of various parameters such as bias voltage or illumination conditions can be used to describe these structures with band diagrams in which the electron affinity is one parameter. For one illustration of the apparent effect of surface termination on electron emission, see Figure 3 in Marchika effect.